Today I would like to talk about the subsea multiple fiber, and this is the agenda of my talk. I will start my presentation with the subsea optical fiber history, a very brief history, and then yes, I will. Okay, and next I will talk about the what is the impact of the digital coherent technology and SDM technology that is utilized for the today's subsea cable system. And then the main topics for the two-core fiber mass production. That what is the design of the our fiber and what is the performance. Also, I will explain about the ecosystem of the two-core fiber system. And I will explain about the future perspective for the subsea fiber as well. Okay, before starting the presentation, who Sumitomo Electric is? Maybe some of you do not know the Sumitomo Electric. We are the Japanese subsea fiber manufacturer. And we started the fiber development in the year 1971, very old history we have. We utilized the VAD method. In 2015, it is selected as the I2B milestone that our honored. And in the year 1989, we supplied world first pure silica core fiber, Z fiber to supply to the Trans-Pacific Cable TPC-4 project. And in the 2014, we supplied the Z plus fiber 130 to the world first transoceanic digital coherent system. And the year 2040, it will be appeared again. So please remind this number. And on the last, the 2023, this year's in September, we announced the world first subsea two-core fiber mass production. We call this a two-core fiber Z plus UL to data. Yes, I think this will be the topic of this today. Okay. So let's move to the history of the subsea transmission. This view graph shows the cable capacity of the historical chart, and various transmission technology contribute to the enhance the cable capacity, and also various fibers, standard single mode fiber, SMF plus DCF. This is the dispersion management fiber. And also the high effective area, only plus T fiber and the two-core fiber today. So what is the message today in this table, in this view graph is new fiber along with the new system had been appeared and also disappeared almost every 5 years. That's very important. Okay, and the next is the digital coherent technology. This view graph shows the historical chart of the transmission loss improvement. And almost 20 years, nothing happened. The loss was very stable. And around 2040, please remind the number. This is a day or year to supply the fiber to the full digital coherent. It encourages us to decrease the attenuation. So if you see this view graph, the attenuation of the mass product and also the R&D decreasing or improved so much. Okay, this is a very important message for the digital coherent technology. Digital coherent technology, the OSNR is the key. So the fiber parameter, the loss is the most important parameter. Okay, and in addition, if you see this view graph, that the solid diamond and the solid circle are the values from Sumitomo Electric. This means that we, Sumitomo Electric, make the history of the optical fiber attenuation. Okay, so what is the SDM, you may know very well. This equation is the Shannon's equation that the transmission capacity is the product of the bandwidth by the log 2 SNR. And for the cable capacity, the product of the channels. So two polarization. This is the X polarization and Y polarization, that P polarization, division multiplexing. And the second term is the SDM channel. This means that the number of cores in a single cable. Okay, today, the number of the fiber in a single tube is increasing. What is the challenge for the optical fiber? The density in a tube becomes higher. So the bending loss can be the issue. For the fiber, the lower micro bending loss is an important parameter for the SDM system. And also the limitation, because of the limitation of the electricity to the optical amplifier, the power into a single core becomes lower. This means that the lower OSNR transmission. This is not very good for the transmission system. So in order to keep the performance, the lowest loss is the most important. Again, okay? And of course, the number of the fiber becomes larger, then people or you ask me to lower cost. Yes, another very important parameter. Okay. So what happened after the launch of the SDM system? This pie chart shows the subsea fiber supply from Sumitomo Electric. In 2018, 2019, just 4 years before, the majority was effective area, the core area of 130 and 150 fiber, more than 60%. What happened 2 years later? Okay. Enlarged effective area fiber is the minority. Okay, so 110 square micron and also the 80 square micron fiber became majority. Okay, so this happens sometimes for the subsea industry, dramatically change of the fiber types. So this is the difficulty of the subsea fiber industry. Okay, investment for the 130, 150 fiber, but just 2 years later, nothing. That's a difficulty. Okay, anyway, we have to contribute to the transmission, subsea transmission industry capacity increasement. So we decide to move to 110 square micron as a majority fiber. This we call that the optimized effective area fiber. Okay. And another importance is this view graph. This view graph shows the designed capacity and the pairs of the core in a single cable. The capacity is increasing steadily, 30% per year. For the pairs of the number of the pairs in a single core fiber, single cable is not so changed before 2020. Before the introduction of the SDM system. Yes, transmission technology improved the cable capacity, but it approaches to the Shannon limit. What happened? SDM. So after 2020, the capacity increasement is depending on the number of the core increasement. So what will happen? 5 years later, the number of the core in a single cable will become 4 times higher. 10 years, 14, 15 years, 50, 20 years, 200. Who guarantee the lifetime of the 20 years of that submarine cable? this is very difficult sometimes. Okay, so now today, people are considering the lifetime of the cable about 10 years because of the capacity shortage. So SDM is very important today's cable, subsea cable industry. Okay, how to increase the core number in the cable? And yes, and if we consider the 1,000 terabit or 1 petabit cable, the year 2026 will be the day. Okay, so how to realize 1 petabit cable? If we consider the one single core fiber, I found a mistake, but yes, that today for the transatlantic cable, that 24 fiber pairs are the real technology. And I make a typo. This is not a tell about the peta, half petabit, 0.5 petabit cabling is today's technology. Tomorrow, maybe slim fiber, 200 micron fiber. If the fiber diameter becomes smaller to 200 micron, the cross-section of the fiber becomes 50% smaller. Okay, this means that the fiber in a single cable or single tube can be enhanced 1.5 times higher. So 24 fiber pairs to 36 fiber pairs. It corresponding to the 0.8 petabit cable, but still not hit to 1 petabit. So how to hit 1 petabit? Simple way, that are 2 core fiber, that are 2 cores in a single fiber. Okay, in the same fiber dimension, the 48 pairs with the 224 fiber pairs can be realized. So the cable capacity will be ramped up to the 1 terabit. So I believe that the 2 core fiber is a straightforward way for a terabit cable. And you may know this is a Google's announcement very recently, boosting subsea cable with multi-core fiber technology. This is for the TPU project. Okay, so subsea multi-core fiber cable is real, not just for the research. Okay, what is our critical performance for the 2 core fiber? Yes, this view graph shows the OSNL penalty as a function of the crosstalk of the 2 core fiber. Yes, that the crosstalk is a new parameter appeared in the 2 core fiber. It is an interaction, the signal transmitting each course. Okay, so if we see this view graph, the penalty from the crosstalk is ignoring around minus 50 to minus 45. So that's a design we shall. And also, the attenuation of the fiber itself is very, very important. If we compare the 0.17 dB per kilometer to core fiber attenuation, this is still not very high. To the 0.15 dB per kilometer to core fiber attenuation. Yes, this is a very low attenuation. It is equivalent to the today's single core fiber attenuation. The penalty is around 1 dB or 0.9 dB. This is huge comparing the crosstalk. So importance is the lowest attenuation of the 2 core fiber. And also, FIFO, this is a fan-in, fan-out device. Insertion loss will degrade the transmission performance. So lowest FIFO insertion loss is another important parameter. Okay, so first, how to mitigate the crosstalk. If the signal transmit parallelly in each course, the coupled signal will become the noise directly. But if each if the signals propagate counter another direction in each core, then first couple to the another core, then back scattering. This back scattering will be the noise. Okay, so the noise suppressed dramatically. Compared to the co-propagation, parallel propagation, the counter propagation suppressed crosstalk by minus 20 dB or less. Yes, typically minus 23 or so. So this is very important. So we adopt this scenario for the optical fiber design. Okay, so the ecosystem. So the importance is to apply existing technology as much as possible, because people want to core fiber technology today. Okay, for the SLTE, you can use the existing. For the EDFA inner repeater, you can use the existing one. So challenging is a two-core fiber itself, of course. And the fan-in, fan-out device. This is the device to divide the two cores into the single cores. This is important device for this ecosystem. And also, of course, the fusion splicing. Yes, if you cannot splice the fiber and to fiber device, nothing happens. And also another importance, and you may concern, is standardization. Okay, and yes, there is no standardization today, but we starting discussion at ITUT, and you can find some very good technical report at the ITUT website. So using this scenario, we announced the world first subsea multi-core fiber mass production. This is a specification of the two-core fiber from Sumitomo Electric. You can download the spec sheet from this URL. Cladding diameter and the fiber diameter is the same as the single-core fiber. So you do not care about the dimension itself. Effective area is the same as the today's 110 square micron fiber. Typical attenuation, 0.158 dB per kilometer. Still a little bit higher compared to the single core fiber, but very low, I believe. Crosstalk, minus 44.3. It is the measured at the supplying bobbin. So it is bent. If it is straight in a subsea cable, it becomes lower, about minus 10 to minus 20 dB. So it is enough number to, I can say, ignore the crosstalk penalty. PMD, 0.2 picosec per square root kilometer or less in a loosely coiled condition. Honestly, this parameter is the most difficult part for mass production. The very initial stage, PMD was more than 1 picosec per square root kilometer. But today, we know how to improve the PMDs. Okay, the proof test level is 200 kPSI. This is for the subsea application. What is the design? We applied the shifted configuration. This means that from the center of the fiber, core 1 shifted to the outer. So this is a, I can say, asymmetric configuration. This configuration have various merits. The core can be identified by the fusion splicer automatically, 100%. We never experienced a failure. But even if we make the long core splicing. This means that the core 1 to splicing to core 2, because of the shifted configuration, splicing loss is very high. Core misalignment is very high. So the splicing loss, we designed as 1 dB or more. So after splicing, you may measure the splicing loss, and you can find, oh, this is a wrong splice. No marker required because the splicer can automatically identify the core. And the free from polarity, this is very important. Yes, if you see the view graph, the polarity free, this means that the two ends have the two on the same phase. Okay, so you can splice a fiber without consideration of the end of phase or the direction. Okay, so with polarity, this is an example for the 4-core fiber. Two ends have different phase. If you make a mistake for the cabling direction of the fiber, then you cannot splice each other. This means that you have to remake the cable, and also thus you have to care about the repair cable direction. This will be very difficult to manage. So by this shifted configuration, easy handling, cabling, and splicing, this means that reducing the total cost, including the repair works. That's a very big merit for you. Okay, so I will show the splicing loss. Right-hand side view graph show the similar splicing between 2-core fiber to 2-core fiber. Okay, the average splicing loss is 0.07 dB per splice. This includes the between the fibers from different preform, not only the same preform. But sometimes people concern about the different lot, different preform because of the change of the configuration. But no problem. Loss, splicing loss is very low. And the left-hand side shows the 2-core fiber to 5-core device. Average splicing loss is 0.10 dB, so it is very low. And the final challenging is the 5-core device. The lowest 5-core insertion loss is the most important for the fiber transmission performance improvement. And this is a OFC technical paper, and insertion loss in a C-band was less than 0.13 dB or so. Yes, this is a hero result. That this is the joint work from Chiral Photonics in the US and we Symmetry Electric. And the size of the device is 3 meter diameter by 60 millimeter length. So compact packaging, we can realize it. And the typical performance of the product is here. Insertion loss less than the typical 0.2 dB. And counter propagation is very low, ignorable. And return loss 60 dB or higher, so ignorable. Okay, this is the ecosystem, so you can enjoy the 2-core fiber cable system today. But still, the improvement is ongoing. Last month, there was the ECOC conference in Glasgow, and the 24 extent of presentation are there. And yes, we Sumitomo Electric also make the presentation to core fiber with less than 0.150, 0.149 dB per kilometer attenuation, very low attenuation. And if you see the loss spectrum, this is very beautiful. because we measured this fiber with more than 40, 50 kilometer straight length. This applied the mass production technology. And sometimes the measurement is not very easy, but compared to the OTDR method, yes, this is equivalent. So this attenuation is real attenuation. And crosstalk, PMD, and also the macro bending loss is very good. So now we are having we are trying to launch this fiber, 0.150 dB per kilometer to core fiber. Yes, now it is under studying. So again, the Shannon capacity with the STM channels. How to ramp up the cable capacity further. For considering the subsea fiber, the ED amplifier is very important. Yes, we know that the bandwidth is another freedom, degree of the freedom. And at the ECOC conference, including for PDP, the multi-band transmission had been appeared. So this means that multi or the broader bandwidth transmission actively studied for the future upgrading the transmission capacity. But as I commented, how to realize the amplification for the long haul system, that will be not very easy. So next fiber will be 4-core fiber, maybe 4-core fiber, because it will appear 5 years later, not very far away. There are so many 4-core fiber candidates. This is a little bit complicated, but uncoupled type and coupled 5 are candidates. And for the uncoupled type, the counter propagation scheme and the co-propagation scheme are proposing. Okay, for the fiber type, uncoupled fiber have the crosstalk. Crosstalk is a penalty. And splicing will be not easy because the core is apart from the center. So very small angle misalignment, very large core misalignment. This means that the high splicing loss. Polarity, as I commented, that these fibers have the polarity. So you have to manage the fiber winding direction, cable direction. And the scalability will be very low because the core is very edge on the cladding. Coupled core fiber. The modal dispersion there is, but this mitigates the non-linearity. This will be the good news. I will show you later. But of course, the DSP load becomes higher. It's not good news. Splicing is easy because it is concentrated in the center. Polarity free. You do not need to identify each core. This is almost a single core type. And high scalability. This year's OFC, we reported 19 coupled core in a 125 glass diameter. Okay, so the high scalability. Yes, and the 7-core fiber, it's easy. Repeater. Okay, the multi-core ED, the counter propagation system, scheme, you need the 5-4 and many EDFA. This is not good news. For the co-propagation, you can adopt multi-core EDFA because the signal moving to the same direction. But this is very difficult, especially the uncoupled type. This is apart from the center. So how to couple the pump to the core? I don't know. Okay. For the dry part, SLTE, Okay, uncoupled type, the today's 2x2 MIMO ASIC can be utilized. Yes, easiest. Nothing to develop. Coupled type, 8x8. This is a 2 polarization by 4 core modes. So 8x8 in total. This is a big challenge. And I would like to ask people to develop this MIMO. Okay, so this is the not very recent that 6 years before transmission experiment, but this is very good experimental result. Using the 4-core coupled core multi-core fiber, more than 1,000 kilometer transmission was realized. And what is important in this view graph? That you see that the coupled core MCL have the better performance compared to the single core fiber. This is because coupled core fiber have the super mode, and it means that the non-linearity is mitigated. So the experimental result shows the Q2 factor of around 0.8 dB improvement. This corresponding to the 32% larger effective area. This fiber has the 110 square micron effective area. So it is corresponding to 140 square micron core areas, very low non-linearity. That's the reason why the coupled core multi-core fiber have the better transmission performance. Okay, so let me summarize my presentation. Subsea 2-core fiber ecosystem you can enjoy today. And also, of course, the fiber performance improvement is ongoing. Future ramp up the cable capacity, I don't know. So subsea industry collaboration is essential. Thank you very much for your kind attention. So any question?
Yeah. So Hirano-san, thank you so much for the presentation. I think there's a lot of great information on it. Could you explain a little bit more about the counter-propagating methodology and also regarding the polarity? What exactly do you mean by polarity in this scheme, please?
Okay, thank you so much. Really? This is a counter-propagation scheme. Okay, the signal transmission the same direction. And the coupling effect is happened. Then this coupled signal can be the noise, the crosstalk to the other red signal. Okay, this is a co-propagation scheme. Counter-propagation scheme, the coupling efficiency is the same as the co-propagation. This is decided by the fiber parameter. But this move to the, yes, this will be the better. The counter-propagation, here the signal transmit to this direction, and the red line, red signal, this direction, another direction. So coupling to the other core. Okay, this cannot be the noise because the direction is different. This is not detected by the receiver. What is important is backscattering of the coupled signal. And the backscattering efficiency is about the minus 20 dB lower comparing to the only the signal coupling. So the noise can be suppressed, or crosstalk can be suppressed by minus 20 dB. And another question is for the polarity. Okay, Yes, this is a little bit difficult. So, if you make the fiber wrong direction into the cable, okay? So the two core fiber, the core 2 will be the upper side, and the core 1 will be the lower side. But if you turn the fiber 180, then the phase is the same as the correct direction. So you do not care about the fiber direction in a cable. This is a polarity free. Okay? For 4-core fiber. If you make the other direction cable, no way to connect the fiber to this one, because the configuration of the core is different from the correct direction. So you have to care about the fiber direction in the cable, and also the repair cable. If you make the mistake of the repair, start of end and the finish end, then you cannot make the splice. That's a polarity. Really, that's okay?
Yep. Thank you.
Okay. Do you have any questions? Okay, nothing.
Yeah, I've got one question. Sorry, could you go back on your previous slide?
This one?
This one, yes.
Okay.
So I presume here you're showing a fiber with two cores.
Yeah.
Which are represented by the turquoise color.
Yeah.
The two transmit sides are using the same wavelength, the same frequency?
Yeah. We are considering the same wavelength, same frequency.
So if, for the sake of the discussion, we're saying that each wavelength carries 200 gig, for instance, just so you've got 400 gig being transmitted on the top.
Yeah.
And the same wavelengths on two different cores, but they interact because of the proximity of the cores.
Mm-hmm.
Now, on the bottom part, you're showing in terms of capacity 200 gig as well. So effectively, the counter propagation is halving the total capacity of your system. That's the part I'm not sure I understand properly.
Okay. So yes, if my understanding is correct, that is there any cross and performance degradation by the coupling effect because the power is losing? The answer negligibly small. Yes, that counter propagation, the coupling efficiency is less than -20 or -30 dB. This means that the power leaked into the another core is negligibly small. So you do not concern about the coupling effect to the degradation of the transmission performance. That's okay? No?
Yes, thank you very much.
Thank you. Okay. Any other questions, comment? Okay, thank you very much again.
Hiran, can you also go to the slides where you were showing the splice loss?
Yeah.
I think
Oh,
Yeah.
This one, okay? Splicing loss.
Also, there was another one where you were showing the specification of the two cores, right?
Yeah,
No, there was, I think, another one more detailed.
more detail. This
Yes,
one?
this one, please.
Okay. Yeah, but this is not a specification. This is a fabrication result.
Okay.
Presented at last week.
One thing I noticed was the cutoff wavelength, right? There seems to be quite a huge variation between core 1 and core 2, right? 1507 and 1413, right?
Yes.
Is that something that you're seeing in the production one as well, or?
I believe this is the fluctuation of the production, not a special meaning.
Well, because you're using C-band, it's not really an issue, I guess, right? But
Yeah, that less than 1520 is important.
Okay. All right.
And the importance is the macro bending loss. And you see the macro bending loss is negligibly small.
Thank you.
Thank you. Any other question, comment? Even a question, comment I will welcome. Okay, so I hope you enjoyed the presentation. Thank you very much.